Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers doing the impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind the scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. Before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid block for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. How can we record brain activity during natural behavior without bulky, restrictive devices? This question has challenged neuroscientists for years, but Saehyuck and Janghwan Jekal from the Daegu Gyeongbuk Institute of Science and Technology, DGIST, have come up with an innovative solution. In this episode of the BCI Award Neurocareers podcast series, we dive into the world of stealthy neural recording with our project, Behavior to Byte, Stealthy Neural Recorder. The team has developed a fully wireless, battery-free, and implantable neural interface designed for primates, allowing researchers to study brain activity during natural behavior without interrupting the subject. This groundbreaking device combines soft bioelectronics for long-term implantation, enabling it to be safely placed deep within the brain for precise neural recording. Join us as Saehyuck and Janghwan share how their research tackles the challenges of developing implantable devices for primates, devices that need to be durable, soft, and operate entirely without batteries. They'll also discuss the potential for this technology to revolutionize neurobehavioral research and offer valuable advice for anyone aspiring to submit a successful project for the BCI Award. Tune in to hear how their stealthy neural recorder is paving the way for more effective brain behavioral studies and changing the future of neural interfaces. Dear Neurocareers podcast listeners, we're continuing our BCI Award series, and today we have absolutely amazing guests from Korea, Saehyuck and Janghwan Jekal. And they will pronounce their names better, but I just want to introduce briefly them to all of you. Thank you very much for coming, both of you. It's a great pleasure to have you on our podcast. And can you please introduce yourself and also tell our listeners where are you joining us from, what institution you are in? So just your background for our listeners. Thank you so much.
Thank you for inviting me. I'm truly honored to be here today. First off, I'd like to extend my thanks to Milena and Christoph Guger for inviting me to join this incredible series. I'm very happy to have this opportunity to discuss our work and share our experience with you all. So, Milena, thank you once again for this opportunity. It's great to be here with you today. My name is Saehyuck, and I'm currently working in my doctoral studies in the Department of Robotics and Mechatronics Engineering at the Daegu Gyeongbuk Institute of Science and Technology.
Yes, hello, my name is Janghwan Jekal, and I'm also currently working on my doctoral studies with Saehyuck in DGIST, located in Daegu and Korea. So he will introduce about his academic journey of himself.
Yes, please. Mm-hmm.
My academic journey began with a major in biomedical engineering during my college years. Yes, now as a PhD candidate, I'm one of the member of the Bio-Integrated Electronics Lab at DGIST, under the guidance of Professor Gyeongjang Jang. Actually, this year is my final year as a PhD candidate, and I am planning to continue my research as a postdoctoral researcher next year. Throughout my time in graduate school, my focus has been on developing and integrating technologies ranging from sensors to devices and systems that can monitor biosignals from various organs and tissues. This includes work in the brain-computer interfaces. I've been involving in developing miniaturized wearable and implantable bioelectronic devices for detecting and treating various diseases. So the work I submitted for last year's BCI Award 2023 revolves around devices and systems that are particularly applicable to the brain. It's an area that's not only fascinating, but also rich with unexplored potential and challenges. I'm excited to discuss more about this research and my journey in today's podcast.
Thank you very much for your introduction. And now, Janghwan, would you like to also introduce yourself and your academic background?
Yes, thank you for introducing me. And I'm also currently working in my doctoral studies in the Department of Robotics and Mechatronics Engineering at DGIST with Saehyuck. And I'm also study engineering and also soft materials and also biointegrated electronics during the undergraduate studies and also now in PhD candidates. And I'm also one of the member of the Biointegrated Electronics Lab, DGIST, under the guidance of Professor Gyeongjang Jang.
Yes, thank you so much for your introductions. And what brought you to the field of neurotechnologies? How did you get interested in brain computer interfaces and neurotechnologies?
I wasn't always interested in neurotechnology or BCI. When I was studying and majoring in biomedical engineering, I wondered why imaging equipment such as MRI and CT used in hospitals or medical devices such as patient monitors have large sizes that can only be used in hospitals. So at the time of my study, I thought that such medical devices had to be large at the expense of patient inconvenience. However, I thought that it would be great if these large medical devices could be miniaturized so that patients could use them outside of hospitals and use them more conveniently and easily. So I expanded on this idea and decided to go to graduate school. In graduate school, I realized that a lot of researchers had already thought about the same thing, and it was still an active area of research at the time. So I got into the field and started to develop devices. Initially, I developed dry electrodes that could be attached to the skin by integrating very thin metal films using fabrication technology with a silicon-based soft substrate. These were used to measure electrical biosignals such as electrocardiogram or electromyogram, replacing wet hydrogel electrodes. I developed not only these electrodes, but also embedded circuit system behind them to amplify, filter, and wirelessly transmit these signals. After that, I was studied neuroengineering research for primates by my professor, which became my main research topic. In fact, it was his suggestion that led me to pursue neuroengineering research. As I mentioned earlier, the idea of brain implant device that can measure and even stimulate brain neural circuits was a good fit for me, as it was an extension of the research I had been doing before. So my colleague Janghwan Jekal and I became the main participants in the brain study. So the brain happened to be a very interesting organ to me. I feel very fortunate to study the brain as a biomedical engineer.
Yes, thank you so much. And what about you, Janghwan Jekal? What brought you to the field of neurotechnologies?
Oh, well, as I mentioned earlier, in my undergrad studies, I study about some mechanics, some materials, and some neuroengineering skills like signal processing skills or some EEG or some neural studies. So after I studied under the Professor Kyung-in Jang, he also suggests me that you, Saehyuck and me, are working together as a team, and you have to study about primates and your engineering techniques for primates during your graduate studies period. So we said, okay, and we're also interested in neuroengineering as a brain because it is so interesting organs that can like we things and we do anything with or do anything with brain. So where we said okay, and we got some lab meetings and we study about these techniques.
Thank you so much. So you are a team. Yes, you are doing things together.
Yeah.
Yes.
Very good, very good. So your project, Behavioral to Byte, Stealthy Neural Recorder, was nominated for the BCI Award 2023. And can you tell about the problem that you were trying to solve in this project?
Yes, the brain is the central organ of the body that orchestrates physical and mental activities ranging from movements to cognitive behaviors. In modern societies, incurable diseases such as Parkinson's disease, epilepsy, depression, and addiction originate from neurological deterioration of the complex brain neural network. So among several animal models, non-human primates, which called NHPs, exhibit phylogenetic proximity and close similarities to humans, and they also provide important translational clinical insights before implementing brain implants on humans. So, but however, most brain neuroengineering studies have been limited to small animal models such as rodents. It is highly challenging to develop a single integrated neural interface system that can record real-time brain neural signals, store data on a server, analyze signal, and combine different device functions into a single implantable device. So our research focused on the development of a wireless, battery-free, and fully implantable device for studying natural behaviors with brain activity in primate models.
Thank you. And Janghwan, do you have anything to add to that?
Most of my answer will be the same as Hello because we work as team. So here's also we were planned to make a device or for neural recorders that can be wireless operating and also battery-free operating and also fully implantable in the primate's brain, also called monkey's brain of monkey. So there are so many things we have to solve, like we have to make a flexible neural probes, and also this flexible neural probe can be inserted into the deep area of the brain. So we have some mechanical tools like cross receptors that can dissolve in the brain in a few minutes, and also we have to produce the wireless power case and also wireless power transfer case. And also we have to make a coil that can receive the power wirelessly. And so the other things like signal processing tools. So that was the problem that we have to solve to study this neural recorder.
Thank you. And what are currently existing solutions? What is already available from those systems that can be integrated into the brain of, let's say, monkeys or big animals?
Yes, in conventional brain neural interface technology, rigid silicon-based neural probe embedded in the brain collects neural signals in a physically restrained or anesthetized environment, and a head-mounted device amplifies, filters, and digitizes those signals. Then wired external equipment extracts features of biological information from these signals. With recent advances in bioelectronics, flexible neural probes, fabricated biocompatible materials, and semiconductor technologies achieve chronic neural signal recording with a minimally invasive approach.
And wireless power transfer and wireless communications design that can enable the design of fully implantable neural interface device, allowing animals to behave naturally in the untethered environments by removing dangerous batteries or external electrical wires. So these technical advancements combined together are currently exist solution for studying natural behaviors in animal models such as primates or the other things like rodent.
Mhm. So, what is missing from current solutions? Why did you start your research? Because obviously you saw that something is missing, yes? So, what is that?
Actually, currently existing solutions, as I mentioned earlier, are the right direction for brain neural interface for animal models. But as far as I know, there have been no fully implantable and battery-free brain implant for primates. Most brain neural engineering studies have been limited to small animal models. So, because there are some technical challenges to apply is current brain neural technology on primate models. First, the brain volume of primates is more than 50 times larger than that of rodents. So due to the large size of the brain, it is difficult to insert a long length neural probe with low bending stiffness by mimicking the brain's mechanical property. And second, primates can sit, stand, and hang in a flexible posture with their forelimbs. So, this freedom of movement is a major challenge in providing stable wireless power. Additionally, most neural interface devices often use a potentially dangerous batteries or short-range wireless power transfer. So these limitations makes it difficult to seamlessly record neural activity for studying naturalistic behaviors.
Overall, due to the aforementioned large animal-specific technical challenge, there is no stealthy integrated those stealthy neural recorders such as integrated wireless and battery-free and fully implantables neural interface for monitoring the brain neural activities of non-human primates' natural behaviors in untethered environments.
Yes, so thank you very much for these details. I'm just very curious because we know, for example, that Elon Musk has the fully implantable and I think wireless system that is used and was used in pigs. It was used also in monkeys. So, what are the differences, let's say? So, the system like this exists, yes? What is different that you are trying to achieve, let's say, comparing with system like developed by Neuralink?
Actually, Neuralink device is the best implantable neural recorder for primates. They have thousands of electrodes and real-time signal recording analysis, but it has a battery inside in the device. So if we implant this device in the monkey, we have to recharge battery or replace battery. It needs very hard work. So our solution is to remove a battery by providing stable wireless power in the monkey's home cage. So this is the main difference. I think this is the main difference from Neuralink.
Yes, yeah, it makes sense. Now it's clear. Thank you very much for clarifying that. So now let's get to your participants, yes, to your primates. Tell us a little bit about them and how you're working with them, how they're helping you in your research.
We know that the other teams that competed with us for the BCI Award have done great research that has been applied to humans. However, there are still a number of challenges in our technology that need to be tested for safety and technical functions before it can be applied to humans. So we applied it on monkeys, which are the most similar to humans. And I think we tested 5 monkeys in total, including 2 different species, macaque monkeys and cynomolgus monkeys. They were implanted with fully functioning devices and kept for up to a month. And all of the experiments were conducted in line with international ethical standards for animal experiments.
Thank you so much. Now, if you can describe your methodology. So, what exactly you were trying to record from monkeys? What type of data? How did you do it? So, if you can provide some details.
Among the diverse behaviors, studying eating behavior in unconstrained conditions is crucial for understanding how organism obtains and during the essential nutrients through the complexly moving behavior. So we select the LHA, as called lateral hypothalamic area, which has been extensively studied over 70 years as the key orchestra of the eating in animals. So we first select the brain area, and next we make the how to insert the neural probe in the brain. So the neural probe was stereotaxically inserted into the LHA of the monkey, and the monkey was moved to the customized wildlife wires home cage for promoting naturalistic behavior without any other wires. So after sufficient recovery period, local field potential was recorded on 32 channels. And a total of 35 eating behavior experiments were conducted, and each experiment was 36 seconds and was divided into phase every 12 seconds, like craving seconds, craving phase, and seeking phase, and consumption phase. And the experiments were for up to 4 weeks, like 1 month. And then recorded neural behavior signals were analyzed through the signal processing with embedded hardware and software algorithm for extracting the distinctive features related to eating behavior phase. Then the gamma power is about 35 to 50 hertz of the LFP was extracted and followed by the calculation of scalograms and band power for further studies. And to analyze these behavior patterns of freely moving monkey for eating behavior, and also we have accelerator in our device. So acceleration data from our device were collected for all eating behavior experiments. And these signals are often utilized to classify movement patterns for like cow or humans or the other animals with several extracted features such as movement variations or average intensity or standard deviations. So we use average intensities and also standard deviation to extract the feature from the acceleration data.
Thank you. So, what helped you to actually create this device that is powered wirelessly? What innovations did you introduce that help you to do that?
Our solution is to use a repeater coil because commonly used conventional wireless power transfer technique uses just one single primary coil for wireless power transfer. But this method can provide power to up to about a few centimeters. So it is not good for primate models because monkey can freely move. So our solution is to use a repeater coil. This repeater coil can be resonated with a primary coil at resonance frequency. So it can produce a more powerful magnetic field. So we can provide a wider wireless power transfer range. So we can apply to primate models.
Thank you. Thank you for clarifying that. And what were the results of your study?
Analysis of local field potentials from electrodes across our 35 eating behavior experiments demonstrated that the average gamma power during the 12-second consumption phase was significantly higher than during the 12-second craving phase. An increase in gamma power during the consumption phase was observed in most experiments and channels. This trend was consistent, whether averaging across channels for each experiment or averaging across our experiments for each single channel. And for acceleration signals in the craving phase, a significantly higher standard deviation in acceleration signals was observed compared to the consumption phase. So by combining these extracted features through a AI model, actually a concatenated layer, the model effectively classifies eating behavior phases. So our data yielded the highest average accuracy of about 90% when the neural behavior signals were segmented with a 4-second time window and 75% overlap. This result suggests that the proposed model using both local field potentials and acceleration data is effective approach for classification of eating behavior phases of primate models.
Thank you very much. What were your conclusions? Did you achieve your goal of your study?
As Saehyuck earlier mentioned, we demonstrate that our proposed Stealthy Neural Recorder is enable real-time wireless monitoring of neural behavior signals and also the analysis of biomedical indicators of non-human primates' naturalistic behaviors. So the developed neural recorder, also called Stealthy Neural Recorder, represent a compact fusion of functional layers with wireless embedded system. The long-length flexible neural probe was inserted into the area region, which is deep brain regions in the non-human primates, using a bioresolver or scrolling shuttles, and also it is enabling the minimal invasive recording of brain neural signals in the deep brain regions. So further enhancing the stats and operate of our neural recorder, we employed the repeater code as he mentions earlier, the based wireless power transfer, which can not only double up it can power transfer up to 60 centimeters. And so this ensures the sufficient and stable operation of the battery-free device across the broad range of uncontrolled primates movements without causing some inconvenience for the monkeys. So through a month-length eating behavior experiments, our neural recorder was utilized to record electric signals and also acceleration data, revealing that significant difference in some bio features across the different phases of eating behavior, like craving and the feeding behaviors. So using biomarkers extracting from recorded neural behavior signals, the AI models that he mentions earlier was achieved about 86% average accuracy, and also highest about 90% accuracy was achieving. So our Stealthy Neural Recorder surpassed the construct of prior pioneering and recording device, offering advanced integrated device solutions capable of studying the innate behaviors primates in a uninhibited manners. So this neural interface opens the possibility of extending the studies of complex neural circuits in non-human primates as a diagnostic and therapeutic tools for challenging the human brain disorder.
Thank you very much. And what was the biggest challenge for you conducting this study, and how did you solve it?
The most difficult challenge in this study was the uncertainty of monkey experiments. I don't know about other countries, but in Korea, the National Primate Research Center was the only research institute that could work with monkeys at the time. And the researchers there had no experience with monkey brain neural signals, so we had to learn everything from the beginning. So not only did we have to buy equipment, create surgical procedures, and plan behavior experiments, but we also had no information on what signals were coming from the lateral hypothalamus area of the monkey. So everything was uncertain. So our solution was to do as much in vitro testing as possible to reduce animal sacrifice and eliminate this uncertainty. So we spent almost 2 years developing and testing without animals, and 1 year on mice, and based on those results, the last year on monkeys. So we didn't plan in this way, but I think this process, even if took us a long time, allowed us to move forward and finish the project successfully.
Yes, so I even didn't anticipate that the project took such a long time to perform. So it was at least 4 years, yes, with testing and probably planning even and conceiving the project even earlier. So it took you considerable time. Yes, yes, great work. Absolutely. Thank you. Then my next question is, what became possible after your study that wasn't possible before?
Well, we expect our Stealthy Neural Recorder to be a platform technology for neural behavior research in primates model, because it can be implanted without the monkey being aware of it, which is called stealthy, and also allowing us to measure the signals while the monkey is engaged in natural instinctive behaviors. So previously, there was no technology to measure the signals for a long period of time with the monkeys who are free to behave studies. So it was essential to restrain them at the end, but our technology is battery-free, so we can conduct experiments in a completely release state. So therefore, we believe that we can most accurately measure and reveal the link between the brain neural activities and behaviors without any other environment factors.
Mhm. And how easy is to implant this technology?
To implant our device, we have to first have to insert our flexible neural probes stereotaxically, and it's easy to implant with our bioresorbable shuttles as we mentioned earlier. And also after that, insert this neural probe, we implant our device under the scalp. So it is, well, it's also first there were so many troubles we have to solve, but now is to implant in our device under the monkey's head.
And how long does it take to implant it approximately?
2 to 3 hours, but it needs imaging of the brain because we have to exactly target the brain area. So we have to anesthetize the monkey and then imaging with MRI and CT. So this time to take more than about 3 hours.
As he mentions, the time that we took MRI image will spends long times because the monkey has to be on the operation tables and there's some MRI mark to implant. And after that, monkey will go to the MRI rooms and to take pictures with MRIs. And then again, it moves to the operations tables. And then we start our neural probe insertions and our neural recorder insertions. So it took about 3 hours or sometimes more than 3 hours because, oh, well, there's some troubles. So yes, it takes about 3 hours.
Yeah. And in this study that you submitted for the BCI Award, what specific areas did you target? You mentioned, but maybe you can just say it specifically. Where did you implant the device?
Our target brain area is a lateral hypothalamus area. Yes, this area is related to eating behavior of the monkey. So we target this area.
Thank you. And how long is the recovery time after the implantation?
It took about 1 week. After the 1 week of recovery period, we took experiments, eating behavior experiments.
And also, how long do you think the device can stay inside the brain and still provide reliable information?
Well, we used this device about 1 month because permissions for the ethics problems, it was about 1 month. But we expect that after we use the other materials or some environments, we can implant more than 1 month, but we use about 1 month to implant. So we didn't do more than 1 month, so we didn't test it. But we expect maybe more than 1 month.
Okay, so you will discover it later on. I'm sure you will continue with this research. So, what were the main innovations of your study?
I think the biggest innovation of this research is integration. In terms of individual technologies, there are neural probes with thousands of electrodes, and there are wireless power transmission technologies with great efficiency, more than our solution. But however, the integration and application of these various technologies to the brain neural interface is another challenge. So therefore, it is significant that we have provided a solution that integrates various fields of technologies, including neural probes, implantation technology, wireless power transmission, devices and communications, and also signal processing and artificial intelligence. So in our upcoming paper, which has not yet been published, there is a spider web graph that visually represents the degree of the integration. And you can see that it is better in terms of integration compared to other existing brain neural interface researches.
Yeah. Thank you. And what are your next steps? What are you planning to do with this study or with this development in the future?
Yes, our next research plan is to increase the number of channels in electrodes from 32 channels to hundreds or thousands electrodes. This is partly about making neural probes more finer, but also we have to use ICs with integrated circuits chips with high number of input channels. So it requires and also wireless communication with a high data rate. So we plan to add a modality with stimulation.
As it says, we also plan to add models that can stimulate the brain instead of just measuring signals like our neural device. So ultimately, our brain implant technologies is not just about measuring signals, but also treating the brain disease. So therefore, stimulations of brain nerves through other methods such as electrical stimulations, optogenetic stimulations, and drug delivery is essential. So by adding these stimulation technologies to the developed measurement platform, we develop an interesting closed loop system. We will begin to develop electronic medicines that also called electrosticks that will enable the treatment of intractable brain disease. And this is next step with our research.
That's a wonderful plan. Now let's get to your BCI award submission. Why did you decide to submit your project for the BCI award?
Yes, either. So actually started with a recommendation from my advisor, Professor Gyeongjak. He received an email from Christoph Kuger about the BCI award and encouraged him to apply. And so he suggested that we submit our research. The BCI award competition in neuroscience was attractive to us because our research was showing good results at the time. And the previous nominations and winners were the leading researchers we already knew, such as Gregoire Putin and Edward F. Chang. So we were confident that it was a very prestigious competition. In fact, I didn't know there was such a competition until then. But after seeing the historical record, I thought that it would be very happy to nominate it here. So I prepared hard for the competition.
Very good, very good. So, what do you think are the benefits of submitting the project for the BCI award?
In fact, it is competitions that is supported and won by world-class leading researchers in the BCI fields. So it is a great honor just to be able to apply the BCI awards and compete with them. And it will be even more the honorable experience if we are nominated and win. So in addition, while preparing for competitions, we were able to organize our research to highlight the main points and advantages to appeal some the other peoples. So we are able to read the directions in which the BCI field is developing by looking at other research projects. So there are many recently published and unpublished studies. So it was a great opportunity to get to know BCI research in advance, like at the conference.
And what advice can you provide to those who are considering submission of their projects for the BCI award to make their submission successful?
Firstly, I would tell them not to hesitate. In fact, when I first visited the BCI Award website and read the descriptions, I was skeptical when I heard that it was the largest BCI award in the world. But after seeing the past participants, my doubts disappeared. I would say that if you are confident in your BCI research, don't hesitate to apply. I'm sure it will be an invaluable experience. To submit for the BCI award, you need to submit a 2-page research summary. In the description, there are questions for scoring, and it's a good idea to structure this summary with answers to those questions, which is what I did. Also, if you make a video to explain your research, you make sure easy enough for the average person to understand, but still show the central technology of your research. I think it's more impactful to use real photos or real videos.
Great advice. And I'm sure our listeners will follow it. And now my question is, what is your advice to those who want to get into the field of neurotechnology and follow your footsteps, creating those implantable devices, innovating the technology? What do you have to say?
The field of neurotechnology, like our research, is a convergence of many different disciplines of science and engineering. And I think our researchers are working in this field would agree that it can never be done alone. It requires so many different peoples to work together to produce results, including mechanical, electrical materials, computer, bio and biomedical engineering, as well as clinical and medical science and neurophysiology. Therefore, if you want to work in this field, the ability to collaborate with these researchers is a very important thing. So you really need to be able to prepare your skills responsibly for a collaboration with other researchers and be able to communicate your needs in a polite and precise manner and be able to organize and design studies and experiments.
Thank you so much. And maybe there is something that I didn't ask you, but you still want to share anything about your research or any advice you want to provide to our listeners.
Thank you for listening to my story so far. It's a great day for me to able to talk to our listeners about my research and the BCI Award. If you are listening to this podcast and you are also a researcher, I am sure you will find a lot of things that resonate with you today. I wish you are the best in your respective endeavors. Stay healthy and enjoy your lives. Thank you.
Very good. And what about you, Janghwan Jekal? Do you have anything to advise or say to our listeners as we end this podcast?
Actually, I'm just still the PhD candidate, so there's not many things to advise because I'm still a student. But I also say that I also agree with Saehyuck that we can collaborate with others, so many other researchers. For example, in our research, like so many doctors and professors and the other student researchers and the researchers help us to complete this project. So you have to study the other things like for the neural studies or brain studies or the biological and also some engineering. So we have to prepare lots of things. And so we have to talk with other people so many times. So that is my advice from my experience. And also I like to say thank you for our listening, for your listening.
Thank you very much. It was a great pleasure to talk to both of you and our listeners and I. We all wish you all possible success in your studies and I hope to see you in our future podcasts, maybe when you already have your implants in humans and helping certain neurological disorders. So I hope to see you again here talking to us. Thank you. Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.org. Come or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you are looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.